So actually, due to COVID-19, my office and the classroom building is closed now. So actually, I cannot go to my office today. So I'm teaching this lecture in the at the home and in my home. So please, even though you can hear some noise from my home, but consider that this is not a normal situation. So okay, so actually the COVID-19 was positive for the graduate student in the of the computer science department. So please be safe and be healthy. uh, so in the today's class, I will complete the lecturing about the exception handling in the pipeline processor, and then I will review the design lab 3. So design lab 3 was to design the single cycle processors with system Verilog. So I will briefly explain how the single cycle processor design can be implemented in system Verilog code. So actually, in order to design the computer hardware processors, you need to convert the diagram or architecture of this processor into the system Verilog code. So you need the translation. So and then uh, the the fourth lab is the final design lab will be out today after this class. So I will briefly explain about this lab 4 assignment. And then I will talk about the simulators for RISC-V ISA. Okay, so in the previous class, we learned about the exception. So the exception is some rare event in the computer processor. So that's why this event is called exception. So what is the normal event in the computer processor? Executing instructions. And the exception means the rare event. So this rare event include some errors in the computer processor, such as the undefined instruction or divide by zero condition, or some rare conditions such as the interrupt. So actually computer system handles the various input and output devices, and then when we use this input and output devices, the interrupt signal is given to the processor if some input or output event happens. So for example, keyboard or mouse is the example of the input devices. So if we uh, put the keystroke, then this electric signal is converted to the interrupt signal in the computer processor, and then the computer processor handles this interrupt event. So you need to know that every operation in the computer system is handled by computer processor called CPU. So this interrupt event should be handled by CPU. So exception is also the same event, the similar event. It's the rare event. So if the exception happens in the processor, then this event should be handled by computer processors. But you need to remember that this exception handling is very similar to procedure calling. So if you understand how the procedure is processed by CPU, then I believe you can easily understand how the exceptions are handled by CPU. It's very similar. Okay. So So for handling the procedure calling, so you need to remember, so how the CPU handles this procedure call. The first, the CPU, actually the code, the instruction code store the return PC, the return location of the code, and then jump to the program counter of the target procedure. And then if the execution of this target procedure is complete, then the PC is restored by the stored PC, the previous, actually some original point, and then the original code is executed in the processor. So, and then that is the same to the exception handling. So we need to store the current PC location in the CPU. Why it doesn't work? So PC is stored in the SCP's register. This is some specific register. So actually in the pipeline processor or single cycle processor architecture, we learned about the general purpose register code, and then this general purpose register is the something like X0 to X31, and then this register's data is stored in the register file. So this is the general purpose registers. But for handling exception, this is the rare case. So this return PC, this program counter data, is stored in the specific register called SEPC. Also, the computer processor need to know why exception happens in the processors. So that is the some cause of the exceptions. So this cause of exception is also stored in the some specific special register called the as cause, the supervisor exception cause register. So if a processor decode the values of the as cause, then the processor can know why exception happens and what's the cause of this exception. So this special hardware is included for handling exceptions, and then the remaining processing or remaining procedure is very similar to the procedure code in the processor. And so you need to remember how the exception is handled in the processor. So exception can happen in at a certain instruction. For example, like add x1, x2, x3. So this is the normal instruction, but exception can be caused by this normal instruction. So what's the very popular exception is the divide by 0. So this divide by 0 exception is caused by divide instruction like div. So when exception happens, then processor is executing a certain instruction. So let us assume that the exception happens by this add instruction. Then in the pipeline, this processor is executing other instructions. So there is the add, then you can find the processing instructions like a sub, like load is a preceding instructions. Also, we can find the following instruction like the next instructions like some mul and store sd. So the exception is caused by this instruction. Then how the processor handles this exception. So we learned that the return address, return program counter, is stored in the SCPCE. Also, the cause of exception is stored in the S cause. Okay, so PC is stored. And how about these instruction? These computer processor need to complete the preceding instructions. So former instructions of this instruction that cause the exception. Then how about this following instruction? So exception means that some error happens in the processor. So if error happens, then the following instruction may receive the wrong data or incorrect data. So if following instructions receive the incorrect data, then these following instructions will generate the also incorrect result. That is, so we need to avoid this situation. So if exception happens, following instructions should be cancelled. So you need to remember this. So this is the how processor handles exceptions. So you need to remember. So processor complete the former instructions, and then for the corresponding instruction, the processor stores the with program counter and then causes of exceptions in the special registers. And then for the following instruction, the processor need to cancel the following instructions, the next instruction. So you need to remember these three different handling operation by the processors. And then, so, and then actually this this kind of exception handling is called the precise exception. So called the precise exception. And then you may expect some another different kind of exception, like exception handling. It's the imprecise exception. So precise exception means that the computer processor can notify the exact location of instruction that caused the exception. And then also the processor can handle the precise handling operation for the exceptions. So that's what I explained here. So this is called the precise exception. But for some very complex process architecture or some, for example, out-of-order processor, then this precise exception is implementing precise exception is very hard, so very difficult. So in this case, the processor supports the imprecise exception. So the pipelining, so the pipeline processor need to implement what I explained. So we need to implement completing previous instructions like here and here, and then flush the following instruction is a flush. Actually, but flush actually for the branch instruction, we already implement how to flush the instructions in the pipeline stages. So we can implement this flush mechanism in the pipeline stages. And then the exception is handled. So, and then exception happens, the processor fetch the new code, and this code is called the exception handler. So exception handler is just very similar to the special function or special procedure. So that is just a group of instructions And then this instruction is also pointed by specific program counter. So when the exception handler is called by processor, then we can just exchange the current PC to the program counter for this exception handler. That's it. So I explained that the exception handling is very similar to procedure call. So if you know how the procedure call is handled by processor, then so you can understand how these exceptions are handled by processors. So this exception handling can be implemented in the pipeline processor like this. Okay, we already explained. And then also I explain how the precise exception is handled by the computer processor. Also, this is the example of the exception and the exception handler code. So this is the program counter of normal code. And then let us assume that exception happens at instruction program counter for C, this add instruction. And then this is the program counter of exception handler. So this exception handler is composed of two store instructions. So this is some specific code. So do not try to understand this exception handler code. So this is just an example code. So let us assume that the exception happens at add instruction in the EX stage. So if add instruction is in the EX stage, then this is the preceding instruction. So or and or. Sometimes it doesn't work. Okay, so or is in the memory stage, and then and is in the write back stage. Add is in the EX and ID instruction fetch. So we know that the computer processor need to complete the or and instructions, and then these sub and load instructions should be flushed. And then for this add instruction, the program counter of add instruction is stored in the SCPs, and then also the code of exception is stored in the scodes register. So you can find this 4C. This 4C is the program counter of this add instruction. So you can find this 4C is stored in the SCPs register. So this you can find the this PC values. So PC for sub instruction is 50, right? It's a 50, and then PC for this load instruction is 54, and then you can. This is the PC 58 is the PC of the very next instruction of this load instruction. Also, you can find this PC of sub instruction here. So the exception is detected. So the computer processor need to call exception handler. So in this example, we can find the program counter of exception handler is the 1C09 blah 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 0000. So this exception PC of the exception handler becomes the next PC of this processor. Okay. So here is the PC. So in the next clock, in the next clock cycle, the the processor need to complete the AND and OR instruction. So OR is propagated to the write back stage. And how about the add instruction? So add instruction caused some errors because it's the exception. So add instruction is also cancelled. So add instruction was here, and then this add instruction is flushed. So in the memory stage, there is no instruction. It's a bubble. Also, these sub and load instructions are also flushed away. It's the bubble and bubble. Also, how about the instruction fetch stage? So in the instruction fetch stage, the processor set the next PC value as 100. This is the PC of exception handler. So the IF stage, this instruction, the first instruction of the exception handler is fetched from the instruction memory. So that's how, so this example show how the exception is handled in the pipeline processor. Okay. So, and then also the more difficult case is the exception multiple exception happens in the different stages of pipeline process. So that is also very rare cases. This is the very rare case because the exception is normally the exception is the rare case, but if the multiple exception happens in the different stage of the pipeline processor, there is a more rare case. So then how can we handle these multiple exceptions? So we can follow the exception handling rule we learned in this class, today's class. So for example, instruction fetch, instruction decode. So it is EX memory and write back. So add, load sub, add, or and load sub and or and. So let us assume that exception happens in the EX stage. Also, exception happens in ID stage. So multiple exception happened. So how can we handle these multiple exceptions? So we need to know what is the preceding instruction when multiple exception happens. So in the program code, the add is the formal instruction of this sub instruction. So when the exception happens, then these multiple exceptions need to be handled in order. So in order, 순서대로. Okay. So because add is the formal instruction of the sub, then the processor need to handle this add instruction with higher priority because this is the formal instruction. So the two exceptions like E1, E2 happens at the same time actually, but different stages. Then this exception 1 has the higher priority. Sorry. Then what will happen? The same exception handling process we learned will be executed in the pipeline processor. So how? the PC of this add instruction is stored, and then the OR and AND instruction is completed in the processor, and then the sub and then load instruction is cancelled. Also, this add instruction is cancelled, and then the exception handler code is called in the instruction fetch stage, and then the instruction handler code complete its execution. Then we return to this add instruction, the original instruction. So the add and actually the instruction starts from this add instruction. Then we can find the sub instruction in the next instruction. Because the add instruction is already executed, then the exception for this add instruction is ignored, and then the sub instruction will also cause exception in the ID stage, because this exception is not handled. It's not handled by processors. So in this case, the exception is handled for ID stage. What will happen? The instructions in the here EX stage is completed, and then this solve instruction, and then the next instruction is cancelled, and then is exception handler for this solve instruction is called by processor. Okay, so that means even though the exception happens at the same time, but the computer processor knows the order of exceptions, also order of the instruction. So the computer processor handles the exception in order. That is the precise exceptions. But in the complex pipeline processor, like out-of-board processor, is very complex and then very complicated, and then the execution order of the instruction is out of order. That means the order of instruction is shuffled. But this out-of-order processor is applied for the high-performance computer processors, such as the laptop or desktop computer systems. So actually, this out-of-order processing is essential for the high performance. But this out-of-order process, because the order of executing instruction is shuffled in the processors, then we can this type of processor is very hard, is very difficult to support the precise exception. So in this case, the exception handling can be supported by software or operating system. So, and then this type of processor just report the cause of exceptions. Okay, so this type of exception is called the imprecise exceptions. So sometimes the processor cannot support the precise exception because this structure of the architecture of processor is very complex, it's complicated. So this type of processor support the imprecise exception. Okay, so now we are done for the pipeline architecture. Okay, and then in the next class, we will jump to the chapter 5, the memory systems in the computer processor. Okay, and then as I promised, I will explain. I will leave the design lab number 3, so single cycle processor design. Okay, sure. Okay, can you see my screen? Okay, thank you. So this code is the skeleton code I posted in the Blackboard. So this incomplete single cycle processor design, and then this code is the it's a complete design. So actually, the student are requested to complete the main control unit, ALU control unit, also immediate generator, program counter, and then several muxes in the single cycle process. Also, students need to instantiate the data path element such as instruction memory, register file, ALU, and data memory. So this is the incomplete code. So this is the the golden code of the single cycle processor. So and then also I'm showing the this is the diagram was it's a pipeline. Let me check where's the single cycle processor design. Okay, here data path with control here. So this is the single cycle process architecture. Then you can find the main control unit here. I need annotation tool supported by Zoom here. Okay, so you can find the main control unit. Then this main control unit generates the control signals here, and then as you can see, this main control unit receives the instruction from pin number 6 to pin number 0, 6 down to 0. So as you can see, you can find this OP code here. So in the main control unit, so this main control unit receives this OP code. So OP code is just the inst 6 down to 0, and then based on the OP code, these control signals are generated. Okay, so branch is, if OP code is like this, then branch becomes 1. Otherwise, branch signal becomes 0. So if you are familiar with the C, then I believe you can easily understand this question mark operation. So this means that I don't know how to. So if OP code equal 0110011, then branch becomes 1. Otherwise, branch becomes 0. Okay. You can find another. Also, we can generate another other control signals based on the OP code like this. Okay. Also, we can generate the ALU OP signal here. So, like if a branch is 1, the branch for the branch instruction, ALU OP, the 0 bit becomes the 1. So this is actually equivalent the branch. So ALU OP 1. If that is the R type instruction, that means the OP code is 1100 or 0110011. Okay. So this is the system value code of the main control unit. It's a simple, right? Okay, right. Okay. Why it doesn't work? Clear. Okay. And then how about the ALU control unit? ALU control unit. So ALU control unit just received the ALU OP signal from main control unit, and then receive this punct 7 and then punct 3 from the instruction. So if we see the, let me see the, so if you see this code, you can find the punct 7 is here, and then function 3 code field is here. Okay. So actually based on the what is here. So we based on this function 7 and then function 3 field, we can distinguish the distinguish the different operation of the ALU. And so you can generate the ALU control like this. Okay. Clear. Okay, clear. And then immediate generator. So actually so in the immediate generator, we need, there are 3 different type of instruction. Is the I type, S type, and SP type. So I type is used for the load instruction. I don't know what is a load. And then S type is the store instruction. And then SP type is used for the branch instruction. So there are 3 different kinds of immediate field. So in this immediate generator code, I first declare the 12-bit immediate value from the instruction. But as you can see, this 12-bit immediate value comes from the different location of instruction, right? So it's a branch. Like this is the SB type. So you can find the branch here. Here. Okay, you can find the memory read means that memory read control signal becomes 1 for the load instruction. So I use this memory read control signal for different immediate field. Also, if not the other case, then we can, this is the S type. So for the S type, so the immediate, the 12-bit immediate value is determined like this. And then we extend this 12-bit immediate value to the 64-bit data, 64-bit signals. And then for the branch instruction, so we need to make this immediate 64 value shifted to the left. Okay, it's also simple. And then let's see the program counter. So this is the program counter code. So in this single cycle processor structure, what the diagram. So this program counter implement the which part? This part. Right. So you can find the PC cur. So that means the current PC, current program count value. So in this slide, so how can you find here? So this is the PC cur. That means current PC, right? Understand? So if this PC current is given to the instruction memory, the instruction memory generate the instruction. So read the instruction from the memory, and then this instruction becomes the output of the instruction memory. So this signal is the PC call, right? So that means this is also PC current, so current PC. Then what is the PC next here? So PC next is the next program counter. So obviously this signal is the PC next. Understand? You may think that, oh, there is no reset or clock signal in this figure, but this is the single cycle processor. So the program counter, so the program counter value changes at every rising edge of the clock. So this PC is the register, and then this PC register receives the clock signal. So it's a synchronized by the clock signal. So this code implement this PC register. So if the reset B signal is 0, then current PC becomes the 0. So that is the reset state. And then this reset state is similar to when you push the reset button in the computer system, your computer system. It's the reset. So reset signal initialize the this computer system. So and then also this reset initialize the every signal in the the system design or computer processor. Okay. So for the initial state, the PC current PC becomes the 0, and then otherwise the current PC is updated by PC next, so next PC value, right? So this is the PC next, updated by the next PC value. So that means in the next clock, the processor received the program counter value is changed to the next PC value. That means the next instruction, and then this processor reads the instruction from the instruction read the next instruction from in the instruction memory. So understand? So you can find these mocks here. So this is the same PC core, and then this is the 4. 이 딜레이를 준 거는 요거는 그냥 시뮬레이션 할 때 보기 좋으라고 한 겁니다. 딜레이를 안 줘도 돼요. 딜레이 안 줘도 되는데 이게 우리가 이제 모델 심에서 웨이브폼을 이게 뭐냐 왜 다이렉트 메시지 잠깐만요. everyone. 예, 이게 이제 질문인데요. 여기서 이제 제가 이제 딜레이 시그널을 준 건데 이 딜레이 시그널 준 거는 그냥 시뮬레이션에서 보기 좋으라고 웨이브폼에서 보기 좋으라고 이제 준 거고요. 이게 왜냐하면은 이 클락이 이렇게 변할 때 사실은 이 딜레이를 안 주게 되면은 여기가 이제 PC 커고 커런트 밸류고 뭐 예를 들어서 이제 0, 0였다. 그럼 바로 요 라이징 엣지에서 요 이제 시뮬레이션 웨이브폼 상에서는 바로 넥스트 요 PC 밸류로 변하게 됩니다. 그럼 이제 사실 이거는 베릴로그 자체는 이게 요 클락의 바로 다음에 클락 라이징 엣지에 바로 다음에 변한다는 걸 알고 있어요. because it's the 델타 딜레이. 그러니까는 눈에 보이지는 않지만 아주 작은 딜레이예요. 그런데 사람이 이게 보기에는 이게 클락 시그널이 먼저인지 요 PC 밸류가 먼저인지 사실 알 수가 없잖아요. 왜냐면 바로 동일한 타이밍에서 변하기 때문에. 그래서 이게 조금만 딜레이가 이렇게 있으면은 요 신호는 요 클락이 먼저 변하고 이 신호가 나오는구나. 이거를 이제 쉽게 알 수가 있기 때문에 그냥 보기 좋으라고 요 딜레이 신호를 넣어주는 거예요. 요 딜레이는 이게 진짜로 구현되는 거 아니고요. 그냥 역시나 웨이브 폼에서 보기 좋으라고 그렇게 넣어준 겁니다. 예. 예. So I will continue the explanation. So okay, here. So this is the PC curve signal. Is the current PC, and then as you can see, here is the adder, and then this add generate the PC curve plus 4. So this is the output signal. So for this output of the adder, so I declare the PC next underbar plus 4. So this is the this is the current PC plus 4. So if you see that this code is assigned PC next plus 4 equal PC curve plus 4. So this is this part. Okay, understand? And then how about the so actually this is the 64-bit immediate value, and then this immediate value is left shifted by 1. So here, so actually this is the here, this part is the 64 underbar branch. Okay, so so here this is the PC curve, and then this is the it's a branch. So this is the adder. So this signal is the PC next branch. So that is the next PC value determined by branch instruction. So as you can see, that is the PC curve. So here plus immediate 64 branch. So do you understand? Clear. And then so you can see this mux here, and then this mux receive the what is this signal? Is the PC next plus 4 here. And then this another input is the PC underbar next branch. And so this mux receive the two input signals and then one selection signal. And as you can see, this one selection signal is the end of branch and ALU 0. So this mux, and then I said this signal is the PC underbar next. So next PC value. So this is the PC underbar next. Okay. So this is the mux. I explained two inputs and control signal. It's a selection signal of the mux. Also, I mentioned the output of mux. Then we can implement this mux. Okay. So this is implement this mux. So as you can see, this is the selection signal. So this is AND, so branch, so control signal, and ALU 0 equal 1, then PC next branch is selected. So this is very similar to the C code. So this signal is selected, right? And then otherwise, that means 0 because the selection signal has only two cases, so 1 and 0. So if it is not 1, then it is 0. Then PC next plus 4 is selected. It becomes the PC next. So understand? And then you can find other muxes here. So actually there are two muxes. So this is the ALU input. So ALU input 1, this is the ALU in 1. So this ALU in 1 is directly connected to the read data 1, the output port of the register file. So this RS1 Dout is the output of the register file. About the ALU in 2, you can find the mux here. So where is it? So this is the ALU in 2, and then based on the selection signal, so ALU source, so this ALU in 2 received the immediate 64-bit immediate value or output of a register file. So this is the mux. So some student post the question about how to implement the mux in the Verilog code. So we can implement the mux module, and then also we can instantiate this mux module in our design. But I said that is somewhat cumbersome. So instead of instantiating the mux design, we can simply implement the mux like this. Okay. If selection signal is 1, then this signal is selected. If not, this signal is selected. So very simple. So we don't need to instantiate the mux design. Okay, so and then finally this mux is implemented here. So you can find the selection signal here. And then this mux received the two input from the read data from data memory, and then ALU result. So based on this control signal, this RLDD is the write data. This RLDD becomes the DMEM, DOut, or ALU result. Okay. So, and then this is the instruction memory address. So I said that the instruction size is the 32-bit. So actually the program counter is the multiple of 4. That means the program counter increased like 0, 4, 8. So multiple of 4. So that means the last, this instruction memory does not require last 2-bit, the LSB 2-bit of the PC value. So that's why instruction memory receive the is the so it's a bin number 2, like a 2, 1, 0 is a bin number. So this bin numbers 0 and 1 is the cancelled, is a throw away, and then this received from the bin number 2. Okay. Also, this is the RS1, RS2 ID. We can this register file receive these values from the instruction, and then how the data memory receive the ALU result from the for the address, and then this ALU result calculate the address of the load or store instruction, and then it's the offset plus base address. So this base address is stored in the register file like x1, x2, blah blah blah, and that's it. And then finally, you can instantiate the already designed data path element here like this. So you can just connect the signal name to the port of data path designs. Like RS1 port is connected to the RS1, ID, IDD, write like here. So you can find the instantiation of the data path elements. And that's it. So it's some example of the hardware design. So in the hardware design, you need to translate. So I said it's translate. So you need to translate this some block diagram or architecture into the system Verilog code. So, and then as I explained, this block diagram or architecture can be mapped to the system Verilog code. So if there is a mux here, we can implement the mux in the code. But there is the header. So the mux here, we can implement the mux code in the system Verilog code in design. Then if there is adult hardware here, we can implement the adder like this. This is the adder. Oh, what happened? So this is the adder, and this is the mux. So we can implement the adder mux in the system Verilog code. So you need to know how to translate your design or architecture block diagram into the real Verilog design for the some digital system design. Okay. Do you have any questions for the lab number 3? Okay, no question. So I believe everyone understand how to design the single cycle process. And then the next lab assignment is to design pipeline processor like this. So in the previous lab's assignment, we designed this single cycle processor. And then this is the 5-stage pipeline processor. Also, we learned why the hazard detection unit and then data forwarding unit is required in the pipeline processor. So I believe everyone understand how to design this single cycle processor. And then this is the 5-stage pipeline processor. So as you can see, we can implement the pipeline register, and then this the flows of the control signals, hazard detection unit, and then the control signals from the hazard detection unit, and then forwarding unit. And that's it. It's simple. But so actually the difficulty of this pipeline processor design is rather higher than this single cycle processor design, because the instructions flows from each stage of the pipeline stages, and then also you need to consider the timing of instructions. So for example, the instruction data flows from instruction fetch to the write back stages, and then the corresponding control signals also go along with these instructions through the pipeline stages. So you need to consider the timing of instructions and the timing of control signals in the pipeline processors. So you need to implement this hazard detection unit and then data forwarding unit. So actually, we learn about the condition of the data forwarding and then the condition of hazard detection unit. So I think that is not difficult, but so you need, but you need to note that. So actually, this is a skeleton code, and then in the lab document, I explain about this packed structure of system logger. So you can read the lab document if the lab assignment is posted on the Blackboard. And then also this program counter. So you need to implement the program counter considering the pipeline stages. So the instantiation of the instruction memory, then you can find here. Also, if you see the code, I distinguish each stage of the pipeline processor, because so from here is the instruction fetch stage. So you can implement the instruction fetch stage here, PC and instruction memory. So it's the instantiation of the instruction memory. Also, this is the pipeline register. So I said that the pipeline register is just a D flip-flop. So at the rising edge of the clock, the input of D flip-flop, that is the input of pipeline register, is updated to the output of pipeline register. So this is the example. So for your convenience, I already implement this instruction if/id pipeline register. This is the pipeline register between instruction fetch and instruction decode stages. So you need to fill this here, but if you see this code, then you can find that. So ID is, for this condition, this ID. So this is the output of this pipeline register. The output of IF ID pipeline register is initialized. So what is this condition? This is not reset state. So for the reset, every output of pipeline register becomes 0. But this is not reset state. What is this case actually? This condition is flush. So pipeline register is flushed. So when this pipeline register is flushed, when we learned 대답 안 하네요. 언제 인스트럭션 패치 파이프라인 인스트럭션 패치 스테이지가 플러시드 되죠? 플러시 되죠? 예상이 틀렸을 때 뭐 그렇기도 하죠. 브랜치 인스트럭션이 taken, 그러니까 브랜치 인스트럭션이 컨디션이 이제 밑에 해가지고 맞아가지고 target of branch instruction으로 갈 때, 그때 instruction fetch 스테이지에 있는 already fetched 된 instruction은 flushed 돼야 되죠. 그때 쓰는 그때 컨디션이 이겁니다. 예, this condition. So this condition means is the pipeline is flushed. Okay. So okay. So this is the kind of control hazard. So that means the branch is taken, then we need to flush the instruction in the instruction fetch stage. So this control signal is generated from hazard detection unit. Okay. So you can find the IF underbar flush. That means the instruction fetch stage is flushed. Also, you can find the IF underbar stall. So that means it's the instruction fetch stage is stalled. So stall means that the instruction remains in its stage even at the next cycle. The pipeline does not go to the next stage. So this pipeline is stalled. So also you need to complete this pipeline. So based on this condition, this id.pc, this is the program counter in the id stage, and then also id.inst is the actually this signal, this inst. So what is different from the single cycle processor? So in the single cycle processor, we directly use the, where is the inst? This inst signal, and then this inst signal is generated from the actually instruction memory. But what is difference? What is different? So actually the output of the instruction memory is this signal. This is the inst. But this signal, actually this signal is called the instruction in this figure, but this is the output of IF ID pipeline register. And then this signal is actually ID.inst. So that means this is the inst signal in the ID stage. So this structure is very similar to the structure of C or C++. And then I already declared the packed structure of the system Verilog here. So you can find the type diff here. So this structure has the member variables like PC and inst. So id.inst means that is the inst signal in the id stage. Okay. So this is the instruction batch and then id pipeline register. And then you can find the instruction decoder staging as an ID stage here, and then you can find the hardware units in the ID stage here. So here's the ID stage. So you can find some hardware units in these stages. Okay. So as you can see, you can find the control unit here. So you need to complete the control unit, but this code will be same. That's very similar to the single cycle control unit of the single cycle processor, because the control unit generates the control signals based on the OP code here. So immediate generate is here. So immediate generate, it's not appear. It does not appear in this diagram, but I know you know. We know the immediate generator is in the ID stage. Okay. Okay, here, and then most important thing is the hazard detection unit. So it's very important in the critical in the pipeline design. So you need to complete this hazard detection unit. I already provide the selection code for this hazard detection unit. So here you can find that the hazard detection unit received some signals here, and then some signals from here, and then generate this signal and this signal like here. But actually, we learned about the store by load use in the class, but we need to implement the store by regular write and branch. So that case is the like this case, add x1, x2, x3, and then PQ receive the x1, x5 target. So what is the problem? This branch instruction received the result from add instruction. The problem is that the branch instruction compares the output of this register file directly in the ID stage. So branch instruction is out of data forwarding path. Data forwarding path is here. So branch instruction cannot utilize the data forwarding unit, data forwarding path in the pipeline processor. That's the problem. So because this branch instruction cannot utilize the data forwarding path, if the branch instruction is here, then we need to store this branch instruction because the data is not generated yet by this add instruction. So you need to also implement these pipeline store conditions for branch instructions. Okay, need to complete. and then this is the flush by branch. That means if the branch is taken, then we need to flush the instruction fetch stage. This is the so flush condition is the you need to complete this signal, this. Also, this is the control signals from hazard detection unit. So I already complete the ID store signal, and then you need to also complete the instruction fetch flush, instruction fetch store, and then this signal PC write. Okay, I think it's a little bit tricky part of this lab assignment. Actually the hazard detection unit design is the tricky part of the pipeline process design. And then also you can find the register file in the ID stage. So here, and then it's this pipeline register file. So you need to implement also this pipeline register file, and then this is the selection code of the ID and ID/EX pipeline register. So I already made this packed structure of pipeline register for ID/EX. So I hope you can easily complete this pipeline register design. And then execution stage, you can find the ALU and then boarding mux and then boarding unit here, the control unit here, and then boarding unit is here. We learned about the boarding conditions in the previous classes, like this here. So this is the boarding conditions. So based on this condition, you can complete the boarding boxes, and then this is the boarding unit. So boarding unit generate the this selection signal, and then this selection signal. Okay, you can implement the boarding unit based on this information. Okay, and then ALU is also in the EX stage, and then pipeline register, and then memory stage. Memory stage is a simple because there is only one data path element in the memory stage here, and then write back stage is the simplest part. In the write back stage, the final result is written back to the register file. So you can implement, complete the write back stage. Okay, so we are a little bit late. So I will stop here. So do you have any questions? So as I mentioned, implementing the pipeline processor is a little bit tricky, is more trickier than the single cycle processor design. So I will give you some enough time for submitting this pipeline processor design, but I recommend you to start early for this lab assignment, the final lab assignment. Okay, and then if you have any questions, post your question on the Piazza, then we will try to answer to your questions as soon as possible. Do you have any questions? Okay, thank you for listening, and then see you in the next class. And then I hope I can teach in the office for the next class. Okay, see you later.